Hello everyone, welcome to the next chapter of drilling engineering, and in this chapter we will talk about wellbore hydraulics pressure drop calculations. So this is chapter 4 of the Adam Burguin book, and if you need more information or reference to go to for calculations and other theoretical aspects of this chapter, you can go to chapter 4 of the book. So we'll talk about the hydrostatics, buoyancy force, pipe tension versus depths, effect of mud pressure, laminar turbulent flow, and pressure drop calculations using both Bingham plastic model and API power law models. So again, this is chapter 4 as I mentioned, and the first thing that we're going to talk about is the hydrostatic pressure calculation, which we already did. So you remember that the equation for calculating the hydrostatic pressure at some specific depths is equal to pressure is equal to 0.052 multiplied by density multiplied by depths, right? So if you have a system that have a uniform density across and then the depth of fluid is some, let's say d, then with the density rho, then you can use this equation to calculate the pressure, hydrostatic pressure at the bottom, which is this point, right? And rho here is, or density is pound per gallon, depth is in feet, correct? So this is the equation if you have one. Of course, you have to add, if you have basically the atmospheric pressure on the top, then you need to add atmospheric pressure as well, right? For example, this system, you can see that there is hydrostatic pressure on the top, so you need to do that as well, have that add. But the pressure gradient, or not gradient, but the pressure differential between this point and that point, if you want to calculate that, then you don't need to consider this, because this is already on the left side, so that's P minus P0, it's equal to 0.052 density depths. Now, if you have multiple fluids inside your wellbore or wherever you are calculating this hydrostatic pressure, then you need to consider each of them separately. So you have a atmospheric pressure on the top, then you have 0.052 multiplied by density of this fluid multiplied by its length, then 0.052 density of fluid 2 multiplied by its length, or height I should say, and so on and so forth. And if you have n of these type of fluids, then your equation in general will look like something like this. You can write it in general this way. So this is an example here. So we want to calculate the pump pressure, which is here at the surface, let's say, and then you have all these columns of fluids with different densities, and this is called the manometer, which you'll learn about this manometer in thermodynamics, but in general this is how a manometer look like, a U-tube shape type of pipe. And you can see here in this area there is a 9 pound per gallon up to this point density fluid, right? And then you have a cement, you have this is a cement slurry, this is not solid cement, so it means that it's liquid, and 8.5 pound per gallon fluid, another 10.5 pound per gallon mud. So this is what happens when you do cementing. Actually we will talk about cementing on the back of the casings, because when you put the casings inside the wellbore, you want to cement them to make sure that it's a complete isolation, and also you stabilize the wellbore. So you inject the cement, you inject another cement, this is a spacer as they call it, and you have the mud on the top as well. So that's how basically you do the cementing. You inject it through to the annulus of the casing and the wellbore. So anyway, we'll talk about cementing later on, but here we want to calculate the pump pressure. So in order to calculate the pump pressure, you can start by considering that this pressure, so you can start from this point at the top. And the way we do calculations for manometers, we start at the top, we go down. As we go down, the hydrostatic pressure increases, correct? And then we go up hydrostatic pressure drops until we reach to this point. So you start from the right hand side of the manometer, you go down, hydrostatic pressure increases, you move to the left side, you start going up, the hydrostatic pressure drops. With what gradient? With this gradient, and here with this gradient increases. So basically you can say that your PA is equal to, you start from the right hand side, this is P0, and then we are at P0, right? Atmospheric pressure at the top, and then we have a 7,000 feet of 10.5 pound per gallon mud, right? So that's plus 0.052 7,000, because the pressure increases, right? You go down, right? Down direction plus up direction negative, right? 7,000 multiplied by the density, and so on and so forth until you get to this point, right? So once you get to this point, the law of hydrostatic pressure is that if you have two fluids at the same, if you have fluids at the same depths, then they have the same hydrostatic pressure. So you can basically from here directly move to here and go up. Okay, so you see here that same equation, 0.052, 10.5 pound per gallon. Then you have a 8.5, 300 feet. Then you have a 12.7, 1700 feet. And then you have a 16.7, 1000 feet. And then you go up. So negative 9 pound per gallon multiplied by 10,000. Assuming that your P0 is 0 psig, then your PA will be 1266, right? So psig again, right? That's gauge pressure. So absolute pressure equal to the gauge pressure plus 14.7 psi. That's basically how you convert the absolute pressure to gauge pressure. So absolute pressure, you show it with psi A, or sometimes just psi, and gauge pressure you call it psi G, as you see here. Anyway, so that's it for hydrostatic pressure. In the next video I'm going to start talking about the buoyancy force.